So we're looking at the Calculus 1 third exam from spring 2024. 6 problems of fun ahead. Let's begin. The graph of y equals x cubed plus 2 crosses the line y equals minus 2x at one point. Estimate the x-coordinate of this point by finding x2 using Newton's method with x0 equals 0. Give your answer as an integer or fully reduced fraction. In other words, simplify your final answer. That's what this really means. Simplify as much as possible. Okay, so what do we have? Well, intuitively, we have two curves, x cubed plus 2 looking like x cubed but shifted up, y equals minus 2x looking like negative 2x but going downhill, and we're after this point of intersection. Okay, so that's the problem. Now, we're not actually finding that point, we're estimating that point, because Newton's method is all about estimation. And in particular, what is Newton's method really about? It's about finding roots. Now you might say, well, wait, that's not a root, that's an intersection. Okay, good. So what are we really doing? Well, we want when does x cubed plus 2 equal minus 2x? So we're going to turn this into a root problem by moving everything to one side and saying we want x cubed plus 2x plus 2 equals 0, and we're going to call this function f of x. All right, so that's our goal. Find the root of this function. Now, quick reminder, how does Newton's method work? Well, it says, hey, if you're looking for a root, then make a guess. And you're probably wrong. That's okay, most guesses are. But what you can do is you can make a better guess. So if here's our initial guess, follow the tangent line down to your next guess. So if this is your guess xn, then if you have your function y equals f of x, your tangent line is y is equal to f of xn plus f prime of xn times x minus xn. Now, your next guess is where y equals 0, and solve for x. That's your next guess. And so, in particular, you get that x is equal to your current guess, and then minus the function at your current guess over the derivative at your current guess. And so that makes your next guess. All right, so that's the generic formula. Just remembering that, that's got to get you some points, right? Oh yeah, oh yeah. Now, what do we need? Well, we have our function, so let's do our computation. Well, we have f of x. We should look at f prime of x. F prime of x, 3x squared plus 2. So, we have our recurrence, xn plus 1 will be equal to xn minus, and f of xn cubed plus 2xn plus 2. F prime of xn, 3xn quantity squared plus 2. All right, now we're ready to go. We know where we're starting. This is our start. We know what we're looking for. That's where we're going to stop. So that says 2 steps. x0 is our initial guess. x1 will be after 1 round. x2 will be after 2 rounds. All right. Well, so let's write stuff down. x0, 0, because that's what we were told. x1 is equal to, now everywhere where you see xn, put 0. 0, subtract. 0 plus 0 plus 2 over 3 times 0 squared plus 2. Well, that's going to be a pretty easy fraction. It's 2 over 2. It's 1. Don't forget the minus. And so minus 1. All right, but we're not done. x2. Okay, so what is x2? Well, x2 is, everywhere we see xn now, put minus 1. Minus 1 minus 1 cubed is minus 1, minus 2, and plus 2. Downstairs, 3 times minus 1 squared, 3, and then plus 2, right? Minus 1 cubed, minus 1, minus 2, plus 2. Good, good, good. And those cancel. Minus a minus makes a plus. So what do we really have? We have minus 1 plus 1/5, which is negative 4/5. That's our x2. Problem done. on to our next problem. All right. Find the area of the region enclosed by the curves y equals 1/2 root x and y equals 1/2 x squared. Okay, so area. Well, let's do a quick sort of sketch, make sure we understand what's going on. 1/2 times square root of x. Well, that looks a lot like square root of x, which looks something like that. So y equals 1/2 square root of x. Now, y equals 1/2 x squared. That looks like a parabola. Okay, so it looks like, and so that's y equals 1/2 x squared. All right, so it looks like they have this sort of intersection going on, right? And, okay, so that's fine. We're after this area. Now, one thing that they didn't tell us is where to start and stop. So we got to figure that out. That's part of the problem. And you might say, is that a problem? That sounds like fun. Good attitude. Right? We should be having fun. So how do we figure that out? Well, when does 1/2 square root of x equal 1/2 x squared? The 1/2s cancel. When does square root of x equal x squared? And you can either reason it out, or if you don't like reasoning, okay, that's fine. You could square both sides. When does x equal x to the fourth? Or 0 equals x to the fourth minus x, which is the same as x times x cubed minus 1. So you get x equals 0, or x cubed equals 1, which is x equals 1. But you could have just come up here and said, aha, I see solutions, and they would have been happy with that. So here's 0. Here's 1. So good news, we know where we're starting and stopping. Which one's on top? That's actually an important thing to think about. So we think it's the square root of x, and we can always pick a convenient number, say like a fourth. Now you might say, isn't a half more convenient? When I see a square root, a fourth is more convenient. Square root of fourth is a half. Half times half is a fourth. Here, a fourth squared is 1/16 times half. It's 1/32. Okay, yep, this was right. Square root's the one on top. Now, we are ready to write our basic setup. Now, how do we find area? We're really finding a total. That is an integral problem. So, our area, the way we find it is we're going to add up from our start to stop, and then we're going to take our height times our width. So, in other words, we're thinking of breaking this up into lots of little teeny tiny rectangles. We're saying, okay, find one rectangle. We can do that. Now, add up all the rectangles, and that's the area. So integration is about adding up. Now, what's our width? Well, that's just a little tiny part right here. That's a small change in the x direction. That's our dx. What's our height? Well, that's going to be the top minus bottom, going from curve to curve. So it's important to make sure you know which one's on the top and which one's on the bottom. So in our case, what do we have? 0 to 1, top 1/2 square root of x. We'll write that in our calculus-friendly way of to the 1/2 power, and then minus 1/2 x squared. I call it calculus-friendly because our rules are x to a power. And so if we want to use our rules, we want to make sure we have x to a power. All right, well, we're most of the way done. It's just a matter of finishing up the computation. So 1/2, we're going to add 1 to our exponent, makes 3 halves. And don't forget to multiply by the reciprocal. It's the same as dividing by 3 halves. So 2/3. Then minus 1/2, add 1, x cubed, multiply by the reciprocal, 1/3. And, well, evaluate 0 to 1. When you plug in 0, good news, 0. Plug in 1, well, 1 and 1. Okay, so what do we really have here? We have a half times 2/3, which is, well, 2/6. A half times 1/3, which is 1/6. And if you put those together, you end up with an area of 1 over 6. That's the area of the region, which means we're done with number 2. Good. Let's keep moving on to our next problem. Compute the following limits. We have 2 of them. Limit as x goes to 0, e to the x minus 1 over cosine 3x minus 1, and then something downstairs. We'll worry about that one later. Now, first thing you always do when faced with the limit is try it. Plug it in and see what you get. Because if you get an answer, you're done. Okay, so are we done? Well, we say, okay, what do we get? This is going to e to the 0 is 1 minus 0 minus 1. Downstairs cosine of 0 is 1 minus 1. This is 0 over 0. And 0 over 0 equals more work. More work, right? Absolutely. So we need to do more work. No worries. We can do that. We'll get that more work done. What is our more work? Well, it is l'hôpital. Oh, l'hôpital, mon ami. Now, before you can do l'hôpital, you actually have to do this check. So if you didn't do this check, they'd be like, oh, why are they doing the l'hôpital rule? Make sure you say, aha, it's a 0 over 0. So now that we see 0 over 0, we're going to go ahead and do some l'hôpital. Ah, l'hôpital. So I'm going to put a LH. That's my way of saying this is l'hôpital's rule. And you can say something much more fancy. And you can say, I am now invoking the l'hôpital rule. Mohohoho. You can make sure you spell out the mohohoho. Otherwise, they won't be sure. All right. Now, here's the great thing about l'hôpital's rule. It's not the quotient rule, right? Oh, the quotient rule is like, how do I remember it? You don't. So you just take the derivative of the top and you take the derivative of the bottom. And it's just like, no, they don't interact. So the derivative of the upstairs, e to the x, derivative of x is e to the x, derivative of minus x is minus 1, and the derivative of minus 1 is 0. Derivative of cosine, negative sine 3x, but remember to do the chain rule, very important rule, multiply by the derivative of the inside. So we're going to throw a 3 in there. Derivative of minus 1 is 0. Okay, well, what is this doing? Well, we're a little bit suspicious, so it's currently going to plug in 0, 1 minus 1 upstairs, and then sine of 0 is 0, which is 0 over 0, which means more work, more work. Oh my goodness, a double l'hôpital. We are lucky. Some people only get to do it once, but this problem is so nice, we're going to do it twice. All right, so, l'hôpital, mon ami. All right, so again, to the top, e to the x. Now, before we go further, what can we say? Game over, man. Game over, right? That's not going to 0 upstairs. Nice. So as soon as, either the upstairs or downstairs is not going to 0 or going to infinity, it's like whatever happens right now. Okay, so we have e to the x. We have this minus 3. And the derivative of sine is cosine 3x. But again, chain rule that. So don't forget to add an extra 3. Okay, so we don't need to check because we see the upstairs is not going to 0. It's going to 1. Cosine of 0 is 1. Then negative 3 times 3 makes negative 9. Or I guess we can write that as negative 1/9. But there you go. All right, part A done. Part B. Find the limit as x goes to 0 plus of e to the power of x log x. Now, the reason they're specifying the plus here is not going to change anything we do. It's just because log x only makes sense for positive numbers. So it's just saying, well, since we have a log of x involved, we have to make sure we keep things positive. Now, how do we do this? There's a couple ways we can do this. Now, one way we could do this is to say, hey, x log x, that's really the same as log of x to the x. So e to the x log of x, that's e to the log x to the x. Okay, well, I got ahead of myself. E to the log x to the x, which is x to the x. and then you could do that limit. But I think what they want us to say is, hey, you know, e is a continuous function. And there's a nice fact about continuous functions. I'm going to make a note here. Now, it's not needed for the exam. You know, you wouldn't need to make this note on an exam, but between you and me. So if you're like, why is he doing this? It's like, oh, he wrote a note. So what's our note? So if you have a continuous function, so if f is continuous, then the limit as x approaches a of f of g of x is the same as f of the limit as x approaches a of g of x. In other words, you can push limits inside. All right, so that's sort of a nice fact about limits. How does that help us? Well, what this really says is that this is the same as e to the limit as x approaches 0 from above of x log of x. Okay, so we need to find this limit. And once we find that limit, remember we're going to take e to that. So we're going to come back to this, leave some space here, and let's work on that limit. All right, so what do we do? Well, we have the limit as x approaches 0 from above of x log x, right? We're working in this smaller space. What does this do? Well, x is going to 0, so this is going to 0, and log of 0 blows up. So it's going to like infinity. 0 to the infinity, which means more work, more work. But wait, it's not the right kind of more work, right? It's not a fraction. If we're going to apply l'hôpital, l'hôpital, what do we need? We need a fraction, 0 over 0, or infinity over infinity. That is not what we have going on right now. So what do? We make it happen. Now, how do we make it happen? Well, we need a fraction. So we have two terms upstairs. One term needs to go downstairs. Now, we could move either term. So the question is, which term do we move down? But I think in this case, it's not going to be a hard decision, because remember that after we move something down, we're going to have to take a derivative. X looks a lot more fun to take the derivative of 1 over x than it is to take the derivative of 1 over log of x. Okay, so with that in mind, we're going to say, hey, this is really the same as the limit as x goes to 0 of log of x, and then downstairs is that 1 over x. So this is the x moved down. Now this goes to upstairs, we still are getting huge, but downstairs we're getting huge. And we're like, yeah, this is our more work that we like. So both of these are signs of more work. But we can't do l'hôpital of 0 times infinity. We can do l'hôpital of infinity over infinity. Oh, l'hôpital, yes! We're going to do this. Okay, so here we go, l'hôpital. We have that this is going to be equal to the limit as x goes to 0 from above, the derivative of log of x, 1 over x, the derivative of 1 over x, minus 1 over x squared. Well, that's the limit as x goes to 0 from above of, move this back upstairs. So it's 1 over x squared, boom, x squared. And so really, negative x, which is 0. I'm like, yes, is that our answer? No. Why not? Because that's this piece. So our answer is really e to the 0, which is 1. And there we go. Number 3, we are done with you. On to number 4. Find the function f of x satisfying all the following properties. So this d squared dx squared f of x is 3 squared root of x. F of x has a horizontal tangent line at x equals 4, and the graph of f of x passes through the point 0, 1. All right, let's think about what these things say. Now, d squared dx squared is just a way of saying take two derivatives. So this could be written as f double prime of x, and 3 squared root of x, Well, we can think of that as 3x to the 1/2. That's the calculus-friendly way to write square root of x. What about number 2? F of x has a horizontal tangent line at x equals 4. What does that mean? It means if we look at the tangent line, it's flat. Well, what's the characteristic of being a horizontal tangent line? It means that we do not move up or down. It means our slope is 0. What tells us about slope? Derivative. So this is really telling us, hey, f prime of 4 equals 0. All right, cool. And then we have the last part. The graph of f of x passes through the point 0, 1. Okay, well that means if we plug in 0, out comes 1. So f of 0 equals 1. All right, now, so what do we have? Second derivative. We want to find function, and we have initial conditions. So great, that's not so bad. In fact, we can do that. We have our ways. We have a plan. So let's start with our second derivative. So okay, that's f double prime of x equals 3x to the 1/2. Now we're going to do one integral. That'll take us one step up the ladder to get our function. So integrating, we'll get f prime of x. Now what will that be? Well, 3x, add 1 to your exponent, 1/2 plus 1, 3/2. Multiply in front, 2/3, right? 1 over 3/2. Add some unknown constant c. Won't be unknown for long. We're going to find it. The 3's cancel, so that gets us 2x to the 3/2 plus c. Now how do we get our c? Well, it's right there. Oh, say, can we find c? Yes, we can with f prime. So 0 equals f prime of 4. Plug in. We get 2 times 4 to the 3/2 plus c. Now, let's think about 4 to the 3/2. We can think of it as 4 cubed, which is 64, square root is 8, or square root of 4 is 2, 2 cubed is 8. Either way, it's very 8. 8 times 2 is 16, so we get 16 plus c equals 0. That tells us that c is negative 16. All right, good. So let's update. So f prime of x is really 2x to the 3/2 minus 16. All right, now that's f prime. We don't want f prime, we want f. So what are we going to do? We're going to do another step, right? So take another antiderivative. So f of x. Okay, so that's going to be 2 times x to the 3/2 plus 1, 5/2, multiplied by 2/5. Now, integral of minus 16, minus 16x plus constant d. Now, it's going to be a different constant, so we should choose a different symbol. So, moving our way up through the alphabet. Well, okay, 2 times 2/5, that's 4/5, x to the 5/2 minus 16x plus d. But we also know that f of 0 equals 1. All right, well, let's use that information to our advantage. We say, okay, well, that says that 1 is f of 0, which is going to be 4/5 times 0 to the 5/2, which is 0, minus 16 times 0 plus d, or d is 1. Aha! Cool! So last thing is we plug it in. So we get that f of x is 4/5 x to the 5/2 minus 16x plus 1. We found our function. It satisfies our 3 conditions, which means we did it, and we're done. And so on to the next problem. Number 5. Find the equation of the tangent line of the function capital F of x, which is the integral from 2x to x squared log of t over t dt at x equals 2. Now, we might be able to integrate. In fact, we can. But do we need to? Well, what do we need? We need 2 pieces of information. And what are they? Well, if you want a tangent line, you need to know two things. You need to know what is f of 2 and what is f prime of 2, because that is going to be what forms your tangent line. All right, well, let's do these separately. Let's start by looking at f of 2. So how do we find f of 2? We plug 2 in. So we say, okay, well, for f of 2, we have the integral. 2 times 2 is 4. 2 squared, 4. Log of t over t dt. Now, do we know what this is going to be? We don't need to find any antiderivatives to answer this. 4 to 4, start equals stop, that's 0. There's no area because there's no width. So, okay, so f of 2 is 0. Ha-ha! Nice! We're halfway to our tangent line. All right, but we also need f prime of 2. Now for that, we're going to say, well, what's f prime of x? Now, that's a derivative and an integral, which means fundamental theorem of calculus. So in general, we will make a little note here. The derivative of the integral from g of x up to h of x of f of t dt, that's equal to, well, f of h of x times h prime of x minus f of g of x times g prime of x. All right, so that's a nice little fact. And so if we have functions here, it essentially says, look, plug the function in and then chain rule through the inside. Plug the bottom function, here we subtract, through the inside. So generically we say, okay, f prime of x is plug the top function in. Log of x squared over x squared. We're not even thinking right now. We're just saying wherever we see a t, we put an x squared. Times by the derivative of x squared, which is 2x. Then minus. Okay, now wherever we see a t, we're putting 2x. So log of 2x over 2x times the derivative of 2x, which is 2. All right, well, let's see. This is log of x squared. And here we can cancel an x. And so we get a 2 over x. And here minus log of 2x. The 2's cancel. And so just over x. All right. Now, that's f prime of x generically. What is f prime of 2? Well, plug it in. That's log of 4, and then times 2 over 2, minus log of 4 over 2. All right, well, really, if we think about it, we can say that, look, this is log of 4, and then we have 2 halves minus 1 half. That's log of 4 over 2, which, by the way, properties of logs, we can move that over to inside. It's like 4 to the half, also known as log 2. So log 2. So there we go, log 2. All right, now we have our function, we have our derivative, and so we can put it all together and say, what's our tangent line? Well, our tangent line would be y is equal to the value of the function at 2 plus the value of the derivative at 2 times x minus 2. Well, we know that that's 0, so we get y is equal to 0 plus f prime of 2, which is log 2, times x minus 2. And there we go. That's our answer. Could we write it in a different way? Absolutely. Would it still be the same line? Probably, as long as we wrote it correctly. And but for now, we're good. Move on to number 6. Consider the area under the line y equals 2x and above the x-axis from x equals 0 to 3. Find the area by using geometry. Geometry. Yes, geometry. One of our favorite subjects. So here we go. We're going to sketch. We'll put some axes here. We're going to have y equals 2x, so it's a little bit steeper than y equals x. And here we're going to go from 0, we'll say here is 3. Now, where is this point? Well, that'd be 6. 2 times 3 is 6. True story. True story. Learned it a long time ago. And all right. Now, we're after the area that's under the line above the axis. And so we say, okay, so we're after this area here, which looks kind of like a triangle. And the reason it looks kind of like a triangle is because it's a triangle. Okay, well, that's a good reason why it should look like a triangle. And we say, all right, so the area, this is a triangle, and it's 1/2 base is 3. So we'll make base, and height is 6. You say, okay, well, 3 times 6 is 18 times 1/2, gets us to 9. Cool. So there we go. Woohoo! We got points. There are points in the house. Woo! Okay, now that's just part A. We have more parts to come. The fun continues. Part B. Approximate the area under the line using a Riemann sum with right endpoints and n rectangles. Your answer should be in terms of n only. Okay. All right. Now, what's the idea? Well, the idea here is we're going to take this region and splice into lots of little tiny slices. So we're going to have n pieces. Now, for each piece, we're going to say what's the area of that piece. We're going to add them up. Now, some good news, we can figure out what is our widths. So our area is going to be our sum. We're going to add up n rectangles. So 1 to n. So we use k as our index. K equals 1 to n. Our widths are, take the total length, so 0 to 3 is 3, divide by how many rectangles? 3 over n. So this is our width of our rectangle. Okay, good to make a note. Now, the trickier part is what is the height? All right, now, you have to pay attention. Where are we looking? The right endpoints. So if we zoom in, say initially we have a 0, and then the first endpoint is 3 over n. Which one are we looking for? Well, we're looking for the 3 over n. Now, all right, what about the next endpoint? Well, we're going to look at 2 times 3 over n. And the next one, 3 times 3 over n, and so forth and so on. So the way we're going to get the height is we're going to have 2 times 3 over n k. All right, now let me just make a comment here. Generically, there's a nice little fact that says if you're going from 0 to a of f of x, right endpoints, then what you can do is that your Riemann sum looks like the b minus a, 0 to a. I usually do 0 to b, so that's why I had a b in my head. So a over n times the sum k equals 1 over n f of a over n times k. So that's just the generic formula. And so that's what's going on here. So this is our a over n times k. And so this is just saying, if I'm at my kth rectangle, I've moved k pieces over. That's all it's saying. All right. Now, unfortunately, we're not done because there's a lot of space, and they left us a very challenging word. Simplify. Oh, no, normally I'm a big fan of simplifying, but I feel like we may have to work a bit on this one. So what are we going to do? Well, anything that doesn't involve k is going to come out. All right, so we're pushing everything that doesn't involve k out of our sum. So 3n, 2, 3n, none of those involve k. You're all going out. You're out of there. All right, so what does that give us? That's 18 over n squared. Sum k equals 1 to n of k. All right, are we done? Well, no, because it says, look, n only. I don't want any k's. All right. So I got to get rid of the sum. Now, there's a handful of sums. Actually, there's like one basic sum that we know. Well, there's two. We know how to add 1 a bunch of times, and then we know how to add k a bunch of times. So the sum, this is just a fact, and so I'm going to write it down on the side. One of these things that you have in your back pocket, you take your n times n plus 1, divide by 2. All right, so here we have 18 over n squared times n plus 1, divide by 2. Now, okay, we're done. We could simplify, right? The 2, we can go and put that into the 18. All right, that would simplify things. And what else can we do? We can certainly cancel out one of the n's. And if we wanted to, we can put this n inside. So this becomes like 9 times n plus 1 over n, which is the same as 9 times 1 plus 1 over n. All right, I think that's pretty simple. Now, last part. Find the exact area under the line by taking the limit of the Riemann sums from part B. Okay, so this was our Riemann sum. This is our estimate. So we're going to say, look, what's our limit? More rectangles. More rectangles, better approximation to area. So we're going to take limit as n goes to infinity of 9 times 1 plus 1 over n. Well, hey, good news. The only place where n shows up is right there. As n gets big, this 1 over n gets small. So our area is 9. And you might say, good, is there a way we could check that? Yes, we can check because it should be the same answer as if we just did geometry. And it is. Coincidence? No. A lot more work to get to 9? Yes. But, it's good to know the theory works in cases where we have a way to check it. And that's it. Right? That's our final problem. We made it to the end. Another great test. Drop the pen. Life is good. And good luck in your studies and keep working hard.